So welcome back. Do you have any questions so far about whatever the little we have discussed today? Because first part of the discussion that we have had so far was non-interactive, unlike what we usually do. So I just thought to give you adequate opportunity for asking questions before I proceed on the second part. Alright, if none, please feel free to ask questions later on. Okay? Fine. So before I talk of WinC, let me ask, as I asked you, a few questions. First question that you would find appearing on your screen is, you may have this question at the back of your mind that why do we need to know which all devices are present inside my target computing device before we begin cross compilation process. Any guess? I'm asking this question specifically for those of you who might have joined late, because for others I have already answered this question initially. Jeremy, any idea? Krishnan, do you recollect? So Krishnan feels that to minimize the OS requirements. Well, that's true in some sense. If you know that you have certain devices inside the, say, your smartphone, etc., that you need to support, you could include support for that during your cross compilation. But if you also know that those are the devices that you have which you will require frequently, you can include this support right as part of the kernel. And if you know that you would use them infrequently, you could make them part of loadable kernel module. All other devices you could leave out of the cross compilation process so that the image size becomes small. Jeremy mentions to enable drivers that we are needed for our final kernel. True. That is also fairly valid a reason. So it's good that both the basic reasons you know. Fine. Now I have a question related to this because we did not discuss this part. If you read your textbook section, or if you have any time installed any operating system yourself and carefully watched while it was installing, specifically Linux and Unix kind of systems, or any OS for that matter in verbose mode, of installation or in command prompt mode, you would know it for sure, but just for the sake of clarity, let me try and ask you this question. I hope you are able to see the second question. If we need to support plug and play feature in the operating system that you are cross compiling from the source, what features or what specific elements or support you need to build at the compilation time so that this feature becomes available, or if that feature for any reason or that capability you cannot ensure at the cross compilation time, what can you do once you have built the kernel image and maybe you are ready to burn that image into your device and then load applications onto it and reboot. Alright, can I, to help you, if you are finding it slightly tricky, okay, this has not appeared. Let me just see. Not yet received. Fine. So I will wait till you see the second point, second question on your screen, and then would expect that you think about a minute and then respond to me. I believe we have started receiving certain responses. Krishnan has mentioned that if we don't have appropriate device drivers installed, then we need to install and reboot them. Okay, you are considering that if at the cross compile time you don't have this awareness, then you will have to do that manually later. Okay, that is the approach you would recommend. I will wait for Jeremy's response also, because there is a better way to do this. Jeremy is not able to see question yet. This kind of surprises me. I have already pressed enter, Jeremy. It's not the problem. Alright, let me do it like this. I will read out the question to you again, just in case you missed. Because what it reads is the following. If we need to support plug and play feature in an operating system that we are cross compiling from the source, right? What all we need to take care of at the compilation time, or if that is not possible for any reason at the compilation time, what can we do after we have compiled to support such a feature? Because one of the responses that I received from one of you suggests that we need to install device drivers later and then we have to reboot. That doesn't help, because it will mean that you are going to install it or you are going to require installing it manually, right? So my question to you is that since most of the desktop operating systems of today already have some degree of plug and play feature, right? And you are starting with the source code which is available to you that has some supplementary and some built-in support of such kind. What care you need to take when you are cross compiling? or if for some reason it still doesn't become available, or you don't have the source code with respect to that particular part, what can you do instead of course, the last route is you have to configure manually and install manually. But if I don't want to take that route, is there a better way to do that? You can think from a typical desktop operating system's point of view and then apply that knowledge to the question that I have asked. So it is important for us to understand some of these things, because certain things that we would study next, not in today's class, but in a class perhaps one more lecture away, and this understanding will play an important role in service level determination. Krishnan suggested that detecting the device first and adding necessary drivers before installation. You are quite right, Krishnan, but if it is to be done manually, then it's not really plug and play feature, right? A plug and play feature would require automatic determination or detection and then if readily available either locally or over the network, automatic installation after downloading the appropriate driver and enabling. And only in case neither locally nor over the network this is available, a manual intervention might be requested by the machine. You got the point, Krishna? So it is in that context that this question comes. Jeremy, maybe you can take at the most one more minute before we move to the third point. In the meantime, let me begin giving some hint. If you take a careful look at the set of features which allow plug and play behavior, what basically such systems which support plug and play do? They have a probe method or probe process, right, which either upon an interrupt gets triggered as an interrupt service routine, or that is when you specifically plug or attach a new device, or at the time when the device starts or restarts, it runs a routine as part of the restart process, where before it initializes certain devices, it tries to first identify the devices which are already plugged in. Beyond the devices which were plugged in and found signature wise during the last run, any new devices that get probed and discovered during the start or restart or reboot period, they get looked for any available drivers which get installed and support enabled without any explicit human intervention, right? So some probing routines either as part of the boot process or post boot process upon generation of an interrupt is required to be there. If suppose none of these are available, you can always write your own program to do this probing, but this probing would make sense only if you have got either the root level privileges or power user or administrative privileges on the machine, because that will be a process which will have a higher privilege process. In typical Linux systems, most of such routines are often written in Python scripts. They are mostly Python scripts, but not necessarily that. I hope I have tried to answer this in one way. There are more ways to answer the same question, but the basic idea remains unchanged, irrespective of whichever operating system it talks about, desktop or embedded. In embedded system operating systems, often such support is provided with a very high degree of constraint, because most of them would not require very large range of devices to be discovered or probed, even if they get attached as peripherals. Also, what external devices can be automatically plugged in while the device is running and could lead to an interrupt being generated and being recognized thereafter also depends on the type of port that you are supporting for external connectivity. For example, if it is a USB port, most of the time such device would be possible to be hot plugged in, right? In certain other cases, that would not be the case. So it depends on the specification of the port also. Specifically, if you are talking about the ports which talk to the devices outside the device body. You are quite right, Jeremy, in mentioning that any specific PNP framework would maintain a list of resources and associated drivers, the registered ones, during the previous runs. All right. So let's now go to the variant of current version of Windows Mobile, or its, which was in form of Windows CE, Windows Compact Edition, primarily designed for embedded devices of varying ranges, right from pocket PCs or PDAs, personal digital assistants of certain kind, to smartphones, to typical miniature robots, to point-of-sale terminals, to set-top boxes, right? Multiple variations exist. The way WinCE and its variants pride themselves is with respect to the kind of flexibility and wide range of platform support. They support, for example, most of the major platforms which you come across in industry. They say that it does support a flexible and adaptable model. Kernel is easily reconfigurable without recompilation, right? And the driver model is simple. Originally this was true. Current model, as you would realize, is slightly trickier than the previous model, but is still usable. And as any embedded operating system would claim, you would find even this one to have support for good power management at the operating system level. Of course, it does benefit from what underlying hardware does additionally support and complement or allows. And of course, over and above the OS level optimization, you as a programmer, even at the application level, can write routines or programs such that which enable or further it. Windows CE or WinCE, as it is popularly called, does support real-time scheduling. We'll see that detail little later. Variant of WinCE, specifically the popular variants were WinCE 3, 5, 6, and of course the current variants. Couple of them remain popular in the market. Interestingly, up to WinCE 5, memory model was fairly limited. In case of WinCE 5 specifically, it did support only 32 processes and 32 MB per processor space. Whereas in case of WinCE 6 and later, you would see not only number of processes supported increased, but the address space in the virtual memory that was permitted per process did also increase tremendously. So what is now supported? 2 GB of virtual memory per process, and as you can see, 32,000 processes, right? This is how the memory model looks like. 2 GB of kernel space, and as we just discussed, 2 GB per process. So the top one shows you the area taken by kernel, file system, windowing system and drivers, right? So kernel file system part which sits on the top of IO subsystem, then the graphical windowing system, then drivers, right? If you see the user space part which is sitting just below this blue marked area, you would have multiple instances of 32,000 processes such that 2 GB of virtual storage is available per process. And what comprises that each of the processes? Memory mapped files of the user, dynamic linked libraries of the user, process code, and the user's virtual memory. User space can be further explored and explained to show the following. It is showing for a single process, this part. You need some area for read-write for the operating system components, but that area which is accessible in read-only mode for the user processes, that area is the shared system heap, which is just 255 MB as per architecture of WinCE, right? Then you have got map files, 256 MB size, and if you notice, these are the ones which are mapped at fixed location, and this has been done interestingly to support those application programs which were designed for WinCE 5 and earlier versions. So for backward compatibility part, right? Otherwise, this limitation was not required to be considered if they could have considered WinCE 6 as an OS which was not required to take care of backward compatibility. But from investment protection point of view, many times such decisions are necessary. Now if you notice, all the code and data which is shared resides here, right? And the rest of the space, actually the rest of the process space is just 1 GB. Though I use the term just as a qualifier, often this is more than enough for most of the common processes that at the user level you would like to execute in such environments. Kernel space, on the other side, has a different mapping structure. Please take a look carefully at the previous one, specifically the top part of it, right? Which was for read-write for OS component and read-only for user process. See, take a look at this and then let's take a look at this. So the CPU specific allocation, right, which is under system trap area. Then kernel virtual memory, which is shared by all the kernel servers and drivers of 256 MB comes next, along with the kernel virtual memory of 256 MB. Please remember, total is 512 MB. How it is supported or bifurcated depends upon what the underlying CPU does enable or doesn't enable, right? If separation is not enabled, whole 512 MB would be available. Now, if you have the need for a file system which is to be built and enabled for manipulation of data in RAM and a small database that you would expect or a registry that you would expect therein, then you would need some specific space, howsoever small that is. It is known here as object store, and has just 128 MB of allocation, right? And the rest of these things are largely self-explanatory, including the static mapped area of 512 MB, which is nothing but a kind of cached access that maps onto the physical memory. So how the things internally work at the architectural level in this operating system? If you notice over here is that at the bottom, as you would expect in any OS, you do have hardware. On the top of hardware, you have drivers, as you would expect. Interestingly, if you carefully look at the second layer from the top, you would again find drivers. So why do you find two types of drivers here? This is because WinCE 6 onward, all versions of Windows CE or WinCE do support two types of drivers. One set of drivers which are most commonly required, they are made part of the kernel space drivers, right? And those drivers which either require frequent changes or are required to be infrequently run and to be used by only a limited set of applications, they are best handled as user mode drivers. This is why they are put at different levels. Of course, as common sense would dictate, anything that runs in user mode would have lower privileges, right? And would have more overheads that they would add. Then apart from that, you have support for network, graphical windowing system, file system, though they would not be exactly directly sitting all of them on hardware, but this is a logical representation of the functionalities shown in terms of modules, right? And then of course, as you would expect, you would have bootloader and the base kernel DLL that you would have. In a way, I could say that this entire part, as shown from here to here, is what typically comprises the core functionalities. On the top of it, there is an interface through which you access this service, which has been shown next, right? And on the top of it, the operating system shell, any user space services, user device space services, etc., work under the control of the applications which invoke them. So in a nutshell, critical drivers, file system, graphical window managers are put into the kernel. You could always ask the question, why a graphical window manager I need to put a part of the kernel? Primarily because when this system boots up, that too to support a specific device which would have a display interface, that would often be required. And as a result, it is best put in such cases right as part of the minimal kernel image that you would like to put, even if you require creating a device specific image for such a case. Another important thing is that the overhead of the system calls between these components could be reduced. Last part is the basic operating system services. If accessed in this way, right at the kernel level, would also allow better code sharing. Let us take a look at the same thing in slightly different way from one of the perspectives. Take a look at this. WinCE 5 and prior variants, what they did, you had separation of applications, services, and what kernel provided, right? So anything that an application required, what happened? Suppose you consider application invokes, let me write it 1, right? Application made a request to kernel let us call it 2, right? This particular line, let me highlight it, that would perhaps help a little bit better. Let me choose a different color. So this particular part, right? We have so far talked in 1 and 2 from application to kernel, and then kernel makes a call to a specific service leading to 3, and when service interacts and returns results, it will come back to kernel, and via kernel it would go to application. So typically 6 steps are involved, right? That is what on the right hand side has been shown. Application makes a call, right? Then kernel gets it, validates parameters, maps services, right? Whatever cache related operations are required, they are carried out, invokes that service, service itself executes. If any results are to be returned, results are returned to the kernel. Kernel then returns the thing by first mapping and any cache operations that it does, and then returns the results to application. What simplification could have been done as per your understanding that makes these set of overheads fairly largely reduced and leads to significant system performance enhancement? Could you think about it? I'm waiting for the response. I received only one response from Krishnan. He says that service can be the part of the kernel itself. All right. Jeremy feels that system call transitions can be avoided. All right. Interestingly, both of you are very close to the answer. Let us see what is the current situation. This is what it is. So if I could move kernel and services both at the same level, right? What is the advantage I do get? Application makes just one call, right? That means application makes a call, that single PSL jump that it leads to, and application need not be mapped again 2 times. So application stays mapped during the call, right? Kernel just validates parameters, which it was doing earlier also, invokes the service, service runs, returns the results. However, instead of returning first to kernel and via that to application, directly to application. So how much is the reduction? If you notice, remember, mapping no longer needs to be had. Let's go back and see this. What did you do? 1, 2, 3, 4, 5, 6 steps are involved, right? Mapping was involved 2 times, right? Where exactly? Once here, and once here. Unlike this, all that you need to do is one-time mapping. And when does it happen? When application makes a call to kernel, that's it. And because map is present, results could be returned directly to the service rather than sending it back via the kernel. So you have reduced context switches also. So as a result, significant performance improvement can be noticed. So as I mentioned, two modes of drivers are supported: kernel mode for when you need highest degree of performance for the most commonly required drivers, frequently required drivers, and user mode when you are looking primarily for robustness, flexibility, and relatively infrequent use. The only thing which differs is level and of course the way client's memory is accessed. So if you are talking of kernel mode drivers, as you would commonly expect by looking into the figure that we have seen earlier, that there is a file called device.dll which loads required drivers in the kernel space, and they have complete access to the data structures maintained by the kernel, right? Key point is this: unlike this, if user mode drivers are to be called in, they are invoked and loaded through user devices, so the called in short udevices.exe, right? Such device drivers, as you would expect by the very name of user mode, do not have access to kernel structures or the kernel's data area in memory, right? So when they would be useful? Suppose there is a device that you do connect to the SD card interface or USB interface as an external device, then they can make sense, right? But if they are the part of the same device which gets shipped, they are better handled through kernel mode device drivers. Performance, if you want to be the parameter with respect to use of those device drivers, you better fit it as part of the kernel mode device driver, right? So this is what the point is: call less often and do more work. So with this we come to the end of today's session. In the very next session, I would pick up, as suggested by Jeremy, Yocto Linux and couple of other Linux distributions case studies, and also pose you to a few problems that such processes would lead to when specifically you want to recompile or cross compile for much more constrained devices than what we have so far thought, for example smartwatches. Alright, so thank you very much, have a nice day, and please take a look at the additional data that would be uploaded to support your assignment over this weekend. Thank you very much.